Thank you for joining in this wonderful event. First of all, let's introduce USF to you all. What is USF? For that, I would like to call Uttam Surpati for introducing USF to everyone. Uttam bhai.
थैंक यू सुरेश एंड गुड मॉर्निंग टू ऑल। मैं उत्तम सुरपति यूनिवर्स साइंस फोरम का कन्वीनर आप सभी जिज्ञासुओं का वेलकम करता हूं इस प्रोग्राम में। यूनिवर्स साइंस फोरम कई सारी साइंस एक्टिविटीज करता है और जिससे कि सोसाइटी में साइंटिफिक टेम्पर डेवलप हो सके, तो उसी का एक पार्ट है संडेज फॉर साइंस, जिसके द्वारा आप अभी ये प्रेजेंटेशन अटेंड करने वाले हो। यूनिवर्स साइंस फोरम एक वॉलंटरी ऑर्गेनाइजेशन है जिसमें स्टूडेंट्स, प्रोफेसर्स, टीचर्स और साइंस लविंग पीपल जो है जुड़े हुए हैं और विविध वैज्ञानिक प्रवृत्ति करते हैं, जैसे कि साइंटिस्ट की जीवनी दिखाते हैं हम स्कूल्स और कॉलेजेस में जाकर, फिर फोटो एग्जीबिशंस अरेंज करते हैं और एक गुजराती ई मैगजीन है जिसका नाम है विज्ञान चेतना, वो भी हम ई मंथली मैगजीन है, वो भी रिलीज करते हैं और जितना हमसे हो सके उतनी कोशिश कर रहे हैं और हम चाहते हैं कि आप जैसे लोग हमारे साथ जुड़े और इन एक्टिविटीज को और आगे लेकर जाए। तो मैं आपसे अपील करूंगा कि ये प्रोग्राम अटेंड कीजिए और जो भी सवाल है वो पूछिए और फ्यूचर में भी हमारे साथ जुड़ते रहिए। थैंक यू।
Thank you, Uttam bhai. So basically, the goal of our event is to develop a scientific temperament in one and all. Before the lockdown, the USF group used to gather at the LD canteen at each and every Sunday for discussing such scientific temperament. But during lockdown, as we have many difficulties, what we came up is with Google Meet platform. We will gather on Google Meet, and every week we will discuss something related to science. Thus, now I would like to introduce to you to our speaker Yash Chauhan. Yash is a second year BSc physics student. For introducing him in much detail, I would like to call his friend Arnav for the better introduction.
Okay, good morning, everyone. So, as you all know, we have gathered here for this presentation on this experimental presentation with the topic capturing the evanescent. So, of course, it is necessary to know something about the speaker first. Yash Chauhan is a really good friend of mine, and he is an undergraduate student in the second year BSc Physics. From the beginning, since we met, he's always been oriented towards research, the research field in physics, and especially in the optical branch of physics. He's always had a orientation in that field of physics, and that has led us today to this presentation. Of course, he has participated in quite several competitions too with me, and of course, he's an active member of the Astronomica, that is the astronomy club of our college. Added to that, he always helps us out of the situations when we are facing some difficulties, of course, in this particular field of optics. So let's get started with this. Over to Yash.
Thank you, Arnav, for this introduction. And thank you, Suresh Bhai, to introducing me. And thank you, USF, for letting me this, allowing me for this presentation. So good evening, everyone, and each and every one present here in Google Meet and YouTube Live as well. Today we will talk about something, a very fascinating phenomena of light, which is frustrated total internal reflection. So the title of the talk, which is capturing the evanescent. I will try to justify this this title and this talk, and I will try. I will promise that at least in this talk we will get to know something or a little bit about what light is or how it behaves differently. So starting with my content, today I will talk about what light is, like what is its nature, how do we know light. the phenomena of different phenomena of light, like reflection, refraction, total internal reflection, which is necessary as of now for FTIR to understand FTIR. There are n number of phenomena for light, but we will study few of them to know our topic. Then I will show how to what is the theory behind the FTIR, or what how to do we calculate those things, how do we do these things. This is particularly for my friend who is in major physics, or who want to know deep about the theory. This is not I will not be deriving anything or doing large derivations, but I will just tell how to do that thing. Then I will show you my experiment, that how I demonstrated using simple equipments and using simple instruments, such home instruments, so that we can get to know this very beautiful phenomena of light. We will discuss its results and conclusion, what will be the data, kind of little bit of data analysis, then its major applications, what are the major applications of FTIR and its uses, obviously. Then I will show what the references and the acknowledgement. So let us start with what is light. So in everyday uses, we used to say that turn on the light or turn off the light during night time. We say that that given bike is having blue color light, or its headlight is orange color light, or its brake light is red color light. So what we are trying to refer is, whenever we say term light in everyday use, what generally want we mean is visible spectrum of electromagnetic radiations. Uh, Whenever we say, whenever we say that turn on the lights, or whenever we generally, well, out of the science, we say in daily uses, we generally refer light, we mean to say is visible light. Visible light means the electromagnetic radiation or electromagnetic wave which falls in visible spectrum of the EM waves or electromagnetic waves. So now we have known that what do you mean, what when we say what is light, what do you mean by saying the light. So now let's talk about its nature. So basically, the nature of light is quite debatable, and it is quite developing as of now. To understand it, there are many theories to understand its nature. So first of all, let us start with the first theory that came up to explain the light. That is corpuscular theory, which was given, I will not say given, because it was earlier than Newton, but which was explained by Newton himself, that light consists of small particles, that reflects off the interface, and that travels in straight lines. So basically, corpuscular theory was successful to say to explain two major phenomena of light, that is reflection and straight line motion. We know that whenever we put object or opaque object between a light source and a screen, we will say a shadow. So what does that mean? That light travels in a straight line. So basically, corpuscular theory was successful in, and we know the mirror, that whenever we incident a light in the mirror, it reflects off. So corpuscular theory was successful in to explaining these two different phenomena, that rectilinear motion or the straight line motion of light, and reflection. But now then comes, along with corpuscular theory, there was another theory given by Huygens. He said that light is a wave. He said that light is a wave. Actually, his theory was not considered at that time, because the corpuscular theory was given by Newton. Because of his name, the wave theory of light was not accepted that much, uh, until the Thomas Young comes up and he demonstrated a double slit experiment. The Young's double slit experiment. We Many of you might be familiar with that experiment. So that experiment basically tells us that why light is a wave, by showing the interference of light. And the corpuscular and it will also explain why corpuscular theory fails. The corpuscular theory fails where if you carefully observe the shadow of a given object, you will see that the edges of the shadow is not properly sharp. You can see still the blurriness of light still there is at a certain depth there is still some light uh, uh, there showing out. So that doesn't mean that shows that light is not actually moving in a straight line. It bends around the object. So wave theory clearly explain that it bends around the object. Then then comes in wave theory. Then comes the Maxwell's equation. It is famously said that the god said Maxwell's equation, and there was light because Maxwell's equation was successful to say that light. We know that light is a wave, but what kind of wave was not answered up until the Maxwell's came up, and until the Maxwell equations came up, and whenever we solve the Maxwell equation we will get to know that this Maxwell equation is what the light is. We verified this equation by getting the speed of light by verifying the theoretical speed and practical speed of light. But then after that, photoelectric effect came up, explained by Einstein himself. So that theory, photoelectric effect, in photoelectric effect, light shows particle nature. So that is again a contradictory thing to wave nature. We know that light is not totally a particle. We can see that it shows interference and diffraction. But in for photoelectric effect and black body radiation explained by Max Planck, for that two phenomena we have to consider, or we have to consider the particle nature of light. Otherwise we cannot explain those two phenomena due to wave nature of light. That debate, or if you want to go in deep, that is very you can say that is very vast topic to see. But obviously yes, after these two experiments, majorly these two and Compton effect and all, the debate again start that what is particle, and introduce wave particle duality, which then gives birth to quantum mechanics. So this is what, as of now, we can say light is. The nature of light is still debatable. It sometimes behaves as a wave, sometimes behaves as a particle. So we can say that yes, particle, wave, light have to dual nature of wave or particle. So now coming up to the third slide. So what are different phenomena? What is reflection and refraction? Because this phenomena will be necessary to understand what our main goal is. That is FTIR, that is frustrated total internal reflection. So in reflection, all of you might have studied in your 10th standard that uh, the angle of incident will be equal to angle of reflection. And the second thing is that reflected ray, incident ray, and the normal are in the same plane. Now let me tell you what normal is. So here is a very good perfect diagram to show this two points, or the law of reflection. The normal is a line at a at a interface perpendicular to the interface where the incident ray is where the incident ray is um, uh, where the ray is incidenting on the interface. At that point, a perpendicular drawn to the surface is what is normal is. Now when this is the flat surface, okay. So if we consider a cylinder, spherical surface, then the normal will be the radially outward at a given point at the surface of that sphere. It will be radially outward, and always in any part of the world, in any part of the given time, if a light ray is undergoing reflection, it will follow these two rules. It is as of now it is seems obvious. It is so it is simple that okay, the light will follow in initial angle equals to reflected angle, and they all three will be in the same plane. But can you imagine that it will be there will be always always at any time this law will be followed. This is not a normal thing if you think deep into it. So now third, then comes the refraction. The refractions obviously will follow the Snails law, which this is also we have studied in our primary level or in the higher secondary schools, that reflect on the light will follow refraction whenever a light is incident into a given surface, and it is and if the surface is transparent, obviously it will follow the Snell's law, and the condition that a reflected ray, incident ray, and normal will be on the same plane. And here is the perfect representation of how this thing will occur. And let me tell you, in every given interface, I'm talking about transparent. As of now, I'm talking about transparent interface. There will be a reflection and reflection occurring at that interface, except for the case of total internal reflection, which we will show in the next slide. In every given interface, because this point will be crucial, and I will tell you how this is crucial in my experiment, and how this will help to demonstrate how to this will help you to calculate the parameters and data for the experiment. Now, going into the third slide, that is total internal reflection. In total internal reflection, whenever a light, wait a minute, whenever light is incident from a okay, whenever a light is incident from a denser medium to a rarer medium, like assume that your light source is somewhere in the water, and it is incident toward the air water surface. You are in the swimming pool, and you are from below the swimming pool, you are incidenting the light. Then at a given at a given angle, that is critical angle, there or at a given angle, the light will travel at a 90-degree along the parallel to the surface. That is what an evanescent wave is. And for an angle greater than critical angle, there will be total internal reflection. So let me say that this condition, that critical angle greater than critical angle, and at a critical angle, this will follow Snell's law. You can apply Snell's law in here. If you see that what Snell's law said is n1 sin I equals to n2 sin r, right? So what will be the n2? N2 will be greater than n1. Now nr, I'm talking about reflected angle will be 90-degree whenever this will be 90-degree. Like if a light ray is passing from a denser medium to a rarer medium, and it is the reflected angle is 90-degree, then we will get a critical angle, and the incident angle will be the critical angle. Here you can see. And for explaining total internal reflection, I would say that how we explain total internal reflection as whenever we incident a light uh, at an angle greater than critical angle from denser to rarer medium, we note that the reflected intensity of light is 100%. 100% means the amount of the amount of intensity we incident on the surface is totally reflected back towards the initial medium, that is denser medium. So that is why we termed it as total internal reflection. But there is a catch here, that it doesn't mean that that light ray is not going into the second medium or is not penetrating into the second medium. Actually, it is going into the second medium. And let me show you this small GIF or GIF. This is a pulse of light going incident at an angle greater than critical angle, and you can clearly see that there is some transmission of light into the rarer medium. That transmission of light, this wave, that portion of light is what we know as evanescent wave, and that transmission of light is only to the certain depth of the second medium. That is what we know as penetration depth of evanescent wave. Let me show you. Let me tell you that evanescent wave will travel along the interface of the given along the direction of the interface, and you can we can see the direction of wave traveling traveling here, that it will be traveling along the interface. So yes, and one the now coming to the visible light, now coming to the evanescent wave. Evanescent wave have certain penetration depth, that it will penetrate the given medium up to which that given level only. And remember that every there is no loss of energy, there is no loss of intensity in penetration of light. It will come back to the initial medium, and this penetration depth depends on what wavelength we use. Like if we use a higher wavelength, then we will have an higher penetration depth. If we use lower wavelength, we will have lower penetration depth. Plus, it will also depend. Obviously, it will depend upon the refractive index of the given relative refractive index of the given to material, and the generation of evanescent wave will only occur if if the incident angle, or if the light source is from the light is incident from a denser to rarer medium, and that too at an angle greater than or equal to critical angle. So these are the few conditions for generating evanescent wave, or having the evanescent wave. Uh, Now, if we see where the visible light falls, if you see, then visible light will be of it consists wavelength of few nanometers only, a few hundred nanometers only. So from that we can see that the evanescent wave will penetrate only penetration and the penetration of the penetration depth of the visible light will be of multiple will be some multiple of the light incident in the medium. Like if we have visible light, as I told you that it is falls in the nanometers, of few hundred nanometers, then the penetration depth of the evanescent wave will also be few hundred nanometers only. So that is where the difficult part comes, that for an optical region, for visible light, catching the evanescent wave or capturing the evanescent wave is difficult. And let me tell you, the first demonstration that this evanescent wave for the first demonstration of catching this evanescent wave was demonstrated in millimeter wave or microwave. We say millimeter wave. It was shown by J.C. Bose, our own Indian scientist. He used alpha prisms to demonstrate. The theory was given. Theory was already been given about this thing, but first demonstration of this capturing this evanescent wave, or FTIR, I would say, was given by J.C. Bose. So he used the alpha prism, and it was first demonstrated in microwave region of the this electromagnetic spectrum. Now going into this FTIR, or what is frustrated total internal reflection. So FTIR, मतलब, how for FTIR there are some conditions. We as we have seen that evanescent wave is penetrating only to few wavelength, or only the penetration depth uh, uh, of the evanescent wave is only few wavelength of the visible, or the given incident light. So first of all, we will in for capturing the evanescent wave, what we will do is we will bring a third medium which will be denser. In this case, we have N1, which is denser medium, N2 will be rarer medium. Let us consider it to be air, which will be the air or vacuum. Then we will have again a denser medium that can be equal to N1, or another other than N1, but should be greater than N2. The necessary condition for FTIR will be that bringing the third medium will be that N2, the N3 should be greater than N2. It can be equal to N1 also. So now, and what we will do is we will bring that third medium in up close to the first medium, that is N1, up to within the range of penetration depth. That is, that if the evanescent wave is generated, that it get transmitted, or it get captured into the third medium, and it can be transmitted. And let me show you the demonstration for this. So this is the light beam. You can this is a you can this is a this is a well representation of a laser beam. This is our evanescent wave going, and this is our third medium where we this thickness should be within the range of penetration depth of the given incident light. You can clearly see that some of the intensity is reflected and some of them is transmitted straight in the direction which it is coming from. So and there are this is the mathematical equation. I would not like we will not derive it as of now. I would like you to consider it now. That this is the equation. This capital T is the relation between intensity of transmitted light and incident light, and we can see that this ratio totally depends upon the angle of incident we are incidenting this light. Uh, Relative refractive index between the this film this rarer medium and denser medium. Then in the thickness of this thickness between these two denser medium, we will as the thickness is very low, then we can consider we can see that this case becomes this becomes the case of thin film thin film. So yeah, yes, this thin film thickness and obviously the wavelength of the incident light will affect the results or affect the intensity of the given light transmitted and reflected. And due to this parameter changes, and due to control of these parameters, we can have whatever intensity we want at transmission and at reflection. That will be one of our crucial you can say crucial application of this phenomena. Now talking about what my experiment sorry talking about the theory, this is particularly for my friends who are in major physics and who want to derive it by themselves, or who want to know what how can we arrive at this given equation. If you want to know how can we arrive at this equation, I would like you to see this flow chart. First of all, we will start with the Maxwell's equation and see and the boundary condition of electric and magnetic field, and and parallel to that we will derive the wave equation of electromagnetic wave parallelly with it. Then with after applying the boundary condition, we will derive Fresnel equation. Let me tell you what Fresnel equations are. Fresnel equations are four major equations which tells us that how much which are the which this equation shows the ratio of transmitted and uh, reflected intensity with respect to incident intensity of light. I would say amplitude, not the intensity. We will get the amplitude ratio between those, and it will be different for perpendicular component and parallel component to the interface. It will be perpendicular to an parallel component. It will be different for perpendicular and parallel component. That is why we will get four equation: two of reflected and two of transmitted, of parallel and perpendicular. Then as you have seen in the previous slide, that we will have the condition of thin film over here. So obviously we will calculate the intensity of thin film and total intensity going total intensity transmitting and total intensity reflecting out. We will calculate those intensities and sum up all these amplitude or intensities to get our total intensity or the amplitude coming out of it. And from the from those amplitude and putting the Fresnel equation in after calculating the thin film summation, what will be the total reflected and transmitted light, we will put this the values of Fresnel coefficients of Fresnel equation, the ratio value, into this calculated equation, and then we will get the intensity relations of the intensities. And here you can see this is not a single equation. If you look carefully, you can see that there is two equations for alpha perpendicular component and for alpha parallel component. So this is for the transmitted intensities. So Similarly, we will have for reflected intensity, and there too there will have two equations for perpendicular and parallel component of the light. So this is how we will come to this equation. If anybody wants to derive or have the glimpse of it, okay, how do we do this? And as of now, we will not do this because it is very lengthy process and very complex process, and it will be very time consuming to do this and will be boring to do that. So we will not do that thing in here. So I have just updated you the how to do that thing. Now, coming to the my experiment. So how did I achieve this experiment or this phenomena in using simple instrument, yet simple yet innovative instruments to show this that there is an existence of evanescent wave, and we can actually extract that evanescent wave, extract or capture this evanescent wave using third medium. Let me show you my experiment. How do we do that? So this will be my apparatus. This is a laser of 532 nanometers, green laser of 532 nanometers. I use protector in order to measure the reflected and sorry the incident angle, as you have seen that the intensity will be dependent upon the angle of incident. And yes, this is one of the most fun part of this experiment. As of this pandemic, I was not able to get hands on the an instrument, or you can say lux meter, to complete my experiment as a sensor, because for sensing the light, that what is the intensity of light, it can be easily measured using lux meter. But as of now, I was not able to get that lux meter. So what I did is, in each and every of as of now, each and every smartphone has this feature of auto brightness. So what does the auto brightness is due to, because each and every of our phone has some light sensor which detects the incoming radiation or incoming light into it, and depending upon that, it changes our brightness. So I use that brightness, or we can use that brightness sensor in our phone to measure the intensity of our light. So and after there are some standard apps, like one of the name is lux meter, or you can just type into the play store, and you will get a lot of app naming lux meter and all, where you can have this proper data that at what amount of intensity is incident in your sensor. Second, there will be some limit in each and every of your phone that it can bear, or the sensor of that phone can bear. So I would recommend you for first of all, before doing this experiment, to see that what will the intensity limit that your phone sensor can bear this thing. Now, now after getting this sensor, after knowing about this sensor, thanks to some people in market, they told me that in phone also you can do this thing. But my second problem was, how did I balance this phone perfectly such that it can, without any support, it gets balanced without any human support. It is perfectly balanced. So what did I do is, I have cut out the soap case in such a way that I can insert my phone into it and tape it up. But after that doing that, but there is one more problem, that the center of mass of this that whole system was not balanced. So because phone is heavier, so it falls down quite frequently. So what I do is, I have attached some thin nails, wooden nails, so that the center of mass of the whole system is easily balanced, and we can have a perfectly stabilized system to like a temporary system to have this sensor, or to, you can say, this whole setup or case, you can see. So yes, these are the nails, and I also inserted some nails inside this to properly balance the center of mass of the whole system. These are the needles, and I have I have taped it tightly, and you can see. Yes, yes. Oh, wait a minute. Sorry. See, this is the app which I have used. It is named as Lux Meter, and this app will tell you the details of the sensor you have in your phone. Generally, the sensor in your phone will be at top right corner or above the front camera, or the above the near the selfie camera. And the thing about that sensor is very very small and very very sensitive, that if there is if the light is not properly incident or if there is some fluctuation of light source or light itself, it will have a drastic change in the intensity. So let me show you first. Yeah, and yes, to check, or I have checked that where the sensor of light is. So what I did is I have put my thumb or anything to block the incident light coming into that sensor, so that we can assure that it will show the zero intensity, that we can assure that our sensor, or that small sensor, will be around there only. You can see whenever I put my thumb, the intensity goes to zero, and whenever I take it out, it will see it goes to zero, as it signifies that my sensor in this phone will be somewhere around here. And yes, it comes back as I lift off the hand, and I use this paper tap to obviously make that case, and secondly to switch on the laser, as my laser pointer is point sensor. Sorry, it has switch off point. So what I did is I put a sellotape around it, so it stays on and on for a given amount of time, and I don't have to switch it on frequently, switch it on and off for frequently. And yes, this is my. Sorry. Hmm. Sorry. I'm sorry for this mistake. Actually. There you go. So
Hello everyone. There is some technical issue with our host, so please stay for some time until the technical issue is solved. Thank you. Till then, whatever questions you have in this talk, you can post in the chat session, in the chat box. Hello, Yash.
Hello. My voice
Yes,
was
yes, you are audible. Wait for some
audible.
time until your net gets stable.
Yes. So
Now
sorry
say
for that.
something. No, no problem. Now you can proceed from wherever you stopped.
Okay. Let wait a minute then. Is my slideshow visible now?
Yes.
I think that video will not work as of now because my net is very slow. I was not able to do that properly.
યસ એક કામ કર યસ તારા લેપટોપમાં કે કોમ્પ્યુટરમાં જ્યાં હોય ને ત્યાં ઓપન કર પીપીટીમાં કદાચ નહીં થશે લોડ નથી લેતો પીપીટી તારું હેંગ થાય છે એટલે લેપટોપમાં જ્યાં સેવ હોય ને ત્યાં ઓપન કર
ઓકે તો જવું પડશે મારે.
ડ્રાઈવ પર કે એવું કશે બી
Yes, yes,
જ્યાં
yes.
તે
ફરી થયું છે પાછું.
વિડીયો માટે તું પીપીટી બંધ કરી દે અને જ્યાં વિડીયો હોય ત્યાં ઓપન
ફરીથી પાછું એન થઈ ગયું મારે એવું છે. જો એક મિનિટ હું ગોતી લઉં ફટાફટ. Is it visible now? Hello? Hello?
Yes, yes, it is visible.
Okay. So yes,
Yeah.
so this is my simple apparatus for introducing the third and our denser and layer mediums. So what I used is I borrowed this clamp from the carpenter. You can get it from any carpenter or any workshop where they use for pressurizing the ply for furnitures. I have used this glass slab, homogeneous glass slab of refractive index 2.5. Sorry, 1.5 refractive index, and I have used them as my denser medium. And the thin film between those two glass slab will be air, and that will act as my rarer medium. And I use this small ply piece as to ensure that there is not much high pressure into my glass, such that it does not break apart, or there is at least I can control the pressure between these two glass slab. And using this screw, I can control the pressure between those two glass slab. So this is basically my apparatus for the experiment. So I will now we will see how we can measure this, how we can measure using our sensor, or we can our sensor or our case, that is lux. How you can measure the lux. Here you can see that I have shown that my sensor of the phone is right next to my front camera, and I'm incidenting my laser light exactly at that point. Even a small fluctuation anywhere, small fluctuation in the table, or in this sensor, or in the laser light, will give a drastic change in the value. So it is necessary to have a very stable for this thing. You can see I am exactly incidenting my light in the sensor, and this is my laser light. And this book also plays a very important role, as this levels up my laser with the sensor, as it is not right next to the ground. So I can level up my light with the sensor. So now we will see total internal reflection. In this condition, I have not pressurized this both glass as to ensure that
યસ તારો વોઇસ કટ થાય છે. કેન યુ પ્લીઝ રિપીટ? હજી એવું જ છે.
Hello, yes.
Hello, Suresh bhai.
हाँ. Hello.
हाँ सुरेश भाई बोलो ना.
Now it is audible. You can continue. Yes.
વચ્ચે અવાજ કટ થઈ ગયેલો યસ.
ઓકે, હવે આવે છે ક્લિયર?
હા હા
હવે
હવે
આવે છે.
કન્ટિન્યુ.
ઓકે, મારે અકાઉન્ટ છે, વાઈફાઈ બંધ થઈ ગયું છે ને ફોનમાંથી છે, એટલે થોડો પ્રોબ્લેમ છે. સો ક્યાંથી કટ થતો હતો પ્લીઝ?
લેઝર
જયભાઈ ક્યાંથી કટ થતો?
લેઝર વાળું પૈતું ને પછી ચાલુ કર. લેઝર વાળું.
આના પછી
આના પછી.
ઓકે આના પછી ને રાઈટ અને આ મેઝરમેન્ટ પછી
હા, આના
કે
મેઝરમેન્ટ
apparatus
પછી.
પછી
ના ના, મેઝરમેન્ટ
મેઝરમેન્ટ
પછી. હા.
ઓકે આ મેઝરમેન્ટ પછી હવે અહીંથી આવે છે ને આટલું થઈ ગયું હતું ને ઓકે so yes this after measure if you we have seen that how to measure this flux or intensity
યશ યશ,
yes
તું હિન્દીમાં બી બોલી શકે છે તને જો કન્વિનિયન્ટ થાય તો વધારે.
હા હા તો વાંધો નહીં મને તો વાંધો નથી but I will try to make it in English
ઓકે ઓકે
अब
ઓકે.
अब एक हाँ so this book is very crucial in this experiment as this helps to level up this laser light with this phone with the sensor of this phone as I have told you that it will have a drastic impact on the fluctuations of the given sensor of the intensity of the light. So now presenting the total internal reflection of light. So at this point, my clamp is not that much pressurized, such that I have not attained the thickness of this thin film between two denser medium is greater than the penetration depth of the evanescent wave. So so that I can get a total internal reflection. I have incident this light into the medium. So you can see that each and every intensity of the light is reflected back. There is no transmission at this point. See, my full intensity is get reflected, and there is no transmission at this level at this point. And as I have told you in the earlier in the slide that it will be crucial to know that each and every transparent medium surface we will get a certain amount of reflection and certain amount of transmission. So you can see that there is a reflection from this point also, and in the glass surface there is a reflection, certain amount of reflection. So our main for calculating purpose, our main incident intensity will be the total as I total which I had shown you earlier uh, minus this reflected intensity. We have to measure for each and every angle. We have to measure this intensity, and that intensity we can get it using Fresnel equation. The incident intensity for our demonstration purpose will be the total which I have measured earlier minus this reflected. So it will give this incident intensity. And you can see the spot over right over here that this is my spot where my light is in interacting with the interface. This is there is no transmission. You can see. Now, showing the frustrated total internal reflection. Here you can see that there is some there at this point we can get there is some transmission of light at this point as I have pressurized this clamp such that the thickness between this air gap between these two glass is up to certain nanometers, so that I can get transmission of light at this point. And for measuring the incident angle, what I used it, I have placed the protector at right above the spot where my light is hitting the interface, so that I can directly see the beam and its measure its angle. As of now in video it is not clearly seen, but when we perform this experiment we can clearly see that there is a light beam which is traveling in the given medium, so we can easily measure the intensity of incident light. And from here we can measure the transmitted intensity also, so that we can verify this data with our theoretical predictions. This is the transmitted intensity. Here is my spot for the interface, and this is my reflected intensity. This is the transmitted. As you can see, it is very much fluctuating as of now because it is very hard to stabilize the whole setup. and even laser, because after certain amount of light the laser become hot, and its initial intensity also varies. So we have to make ensure that this variation of intensity is not wide. So we have to cool down to let we have to let the laser cool down for certain amount of time, so that we can get a constant intensity, and there is no variation in our data. So that's all for this video. Now let me back to the presentation. A minute. So wait, let me present my screen now. Can you see my presentation?
Yes, yes.
Can you see my this data comparison graph shows my result, that how the changing angle of incident give rise to decreasing the intensity of the light. This blue line represents my practical data, and this red line represents the theoretical data.
Hello, Yash.
हेलो सुरेश भाई.
हाँ तारो अवाज कट थतो હતો હવે પાછું કન્ટિન્યુ કરો.
Okay. So yes, this data chart represents how well, or this data chart represents the theoretical prediction and practical data set. As my experiment was, my instruments was not that much precise. You can see that this practical data, the blue line data, predicted theoretical data, that how should the practical data. But the problem is that the instrument was not that much precise to measure the intensity. As we increase the incident angle, we will get the change in intensity ratio, or the intensity of transmitted wave. Uh, and the range set which I have taken, that data is 60 to 70, which will be for this instrument will be because of the less precise instruments, I can say. And yes, the conclusion for the experiment confirms the of light. This experiment will show how we increase when we increase the angle of incident, the intensity of the transmitted light decreases, and henceforth become the one of the valuable experiment in UGPG solution to explain the wave nature of light. So yes, this experiments helps us to understand that there is the existence of evanescent wave, to study the evanescent wave, and yes, obviously it is one of the conclusion to say that the light will have a wave nature. And its major uses and application is that it is direct analogous to quantum tunneling effect, and in which we have seen that the particle is you can particle is tunneled through a barrier which barrier it. So this is a quite its major application is considered splitter, as many of my friends have known that. Manu bhai, आपको hello, hello, okay, sorry. Hmm. So the one of the most major application of this FTIR is beam splitter, and as I told you while we have seen that equation, depending upon the parameters, depending upon the wavelength, depending upon the relative refractive index, angle of incident, this the intensity of transmit and reflected light can be easily vary, and we can get what we want, like 30% of the light should be transmitted and 70% should be reflected. We can get this variation easily, so that so that we can get the required amount of light we want. Or in fact, the advanced beam filter uses polarization technique also to get required polarization. And yes, the fingerprint sensor in our phones and is will consist the basic basically, due to which we can sense the pattern of the fingerprint. And in daily life, you can observe this FTIR easily in while holding cold water glass, where whenever we hold that cold water glass, we can transparent cold water of glass, where we can see the temperature of our fingerprint, and that impression is basically due to this FTIR phenomena, because the finger are approximately near or within the range of penetration depth, so such that we can see our skin itself. And these are my references. These are optics by AJ Katak and Pedrotti, Frankel Pedrotti, to get my theory completed. And these are the two scientific articles which I have used for for getting the idea of experiment. And I would like to thank my parents for helping me out and for motivating me, always motivating me, for having the such scientific knowledge. And especially to Dr. Pandya, as he is the one he has topic in my mind, and he helped me to clear out this is very I will say you that it is very complex to achieve the derivation of equation, and due to Tushar Pandya, I was able to explain this theory. And I was it was very sad that he is no more with us, and he was not able to see actually this experiment, as I have completed this experiment after his death. And I would like to thank Universe Science Forum for helping me and supporting me, and providing me this platform to give a talk. And obviously, I would like to thank my seniors, Jahan Bhai, Kishan Bhai, and group, and colleagues Jatin, Arnav, for helping me out for this talk, and everything after this. So thank you for the opportunity.
Thank you so much, yes, for such an amazing talk. The experiment you set up was was so interesting to see, as you overcomes many obstacles for creating such an amazing experimental setup in lockdown at your home. So that's so amazing. Now I would like the participants, if they have any questions, you can ask to yours. You are open to ask. Anyone? You can even type the question in the chat box also. Okay, so Uttam Bhai is asking, can you tell once again the name of the crystal used by J.C. Bose in his experiment of FTIR?
I don't know the name of the crystal, but as per my knowledge, as per what I have read, they have used alpha prism. That is the only information as of now I have. Sir, JC Bose have used alpha prism for measuring the or to getting this to get this experiment of FTIR. You can actually you can have this information about the proper crystalline structure or proper crystal for this experiment from the net. It is in Wikipedia. It is very well explained about this experiment because the crystal as per my knowledge, the crystal should be transparent with respect to microwave medium microwaves range. The range of the crystal should be transparent with respect to microwave range. And yes, that's all as of now I know about the experiment. And
And Jay is
and
asking,
yes,
is it
Jai,
necessary to have TIR for FTIR to happen?
uh, yes, because without that, how we will generate a evanescent wave? Because what FTIR does is it captures
Your voice is not clear, Yash.
Hello.
Wait a minute. Wait a minute. Hello. Is it now
Audible.
clear?
Yes, yes.
Hello. Okay. So Jaibai, yes, it is necessary to have TIR because at that time only we will be able to produce evanescent wave. Because what FTIR does is that it directs or it captures the evanescent wave generated in the FTIR in the experiment of TIR. So yes, you can say that TIR is necessary, and obviously the FTIR is a second step to TIR. You can say. Any more doubts, please?
And no, no, thanks. And last one, I would like to ask that there was a class example that you gave in the end, the class you were holding. So I would like to ask that was there any TIR of your light coming from your fingers?
Yes,
So the
wait a
no,
minute.
so the one the dancer, the first there was air in which your fingers are there. Then there is a glass, and then there is a
Mm,
water.
mm,
So
yes.
I would like to ask, where are the two denser mediums? Like with the glass one is denser and the water is another denser. So there is you are telling that air is between that water and the glass
See,
touching.
See, actually, in the specification for I would say specifically cold water, because there is condensation of water beyond the glass, our glass or whatever the plastic we are holding in. So the thing is, the water, the condensed water around the glass at third denser medium, that this FTR happens where our water, the water medium in the fingers. First medium you can say is the glass, and
हेलो।
did you get it?
યસ, તારો અવાજ એકચ્યુઅલી કપાઈ ગયેલો, તું બોલતો ત્યારે.
Hello, is it audible now?
Yes, yes, it is audible.
Okay. Yes. So the condensed water outside the glass will be your third medium, third denser medium. The air inside, in your fingerprint gap or in the fingerprints gap will be your thin film, and that the glass, the material which we it is made up of, the transparent material, it can be plastic or thick glass. The thick glass will give very good results. So that will be your first medium, first denser medium.
Hmm.
And let me show you that thing where the total internal reflections also occur. Wait, can you see my slide?
Yes, yes.
So yes. So can you see this area above the fingerprint impression?
In glass?
Yes, yes. Can you see my arrow, my cursor?
Yes, yes.
So you can see that there is a finger right around next to it, but still you can see that finger. But here you can see is the fingerprint impression, because as I told you that here there is total internal reflection occurring everywhere
Hmm.
around. And whenever we are pressing our hand between in the glass, we, as I told you, that there will be three medium. So at that point we will get FTIR, and we can see that transmitted light which is transmitted in the third medium will reflect back from our hand, uh, and we can see that reflected light as a fingerprints of our impression of our fingerprints. Did you
Acha.
get it? Did
Yes,
you
yes.
get it? Okay.
Yeah.
So the cool water is the key part for that thing to happen. So cold water will be the necessary key part. Anything else, please? Anything natural? Naturally, I don't think so. Any natural phenomena is there for FTR, but yeah, there's you can consider this glass example as natural phenomena. But in nature, I don't think so. This happens. As per my knowledge, I don't think so. If I may be wrong, but as per my knowledge, I don't think so. There is a example of FTR in nature.
Okay, so anyone has any else questions? તો યસ મેં તને ક્વેશ્ચન પૂછ્યું કે
Mhm.
મેં જે આખું એક્સપેરિમેન્ટલ સેટઅપ કર્યું એમાં તને કયા ચેલેન્જીસ આવ્યા તે તું પેલા કે
No. First of all,
એક્સપેરિમેન્ટ તારો ઈઝી હતો નહીં ને ઘરે પરફોર્મ કરવું ઇટ વોઝ સચ અ ડિફિકલ્ટ ટાસ્ક કયા ચેલેન્જીસ આવ્યા ને કેવી રીતના તે ઓવરકમ કર્યા.
yes, the first and foremost thing was to how do I get this thickness of minimum thickness of nanometers to attain nanometers ની thickness જોઈતી હતી ક્યાંથી મળે. So એના માટે solution was that I should press जो ग्लास वाटर में अभी हमने देखा कि हम जो अपनी उंगलियों से दबाते हैं जो टाइटली दबाते हैं तभी हमको मिलता है. So the idea came that there should be some pressure between those two mediums which I am using. So उसके लिए बाद में ये क्लैंप का आइडिया आया कि कारपेंटर यूज करते हैं प्लाई को चिपकाने के लिए. सो ये पहले क्लैंप का आइडिया आया कि भाई 2 ग्लास हो तो उनको क्लैंप से दबा सकते हैं ताकि उनके बीच के गैप कम हो. अभी दैट टू ग्लास शुड बी plain, well cutted and well polished. Then and then only we can get this thing of proper space between them. Otherwise, there will be problem. Otherwise, we cannot get this minimum distance we required. So yes, this first challenge was this. Second challenge was obviously the sensor. As I was not in my, I have no access to the lab in our college, so I was not I don't have the access to the sensor. And yes, at that time Tushar sir was also busy in his work, so even he was not able to help me out for this. And so what I did is I've roamed whole of the my city, मतलब पोरबंदर पूरा घूम के मैंने देख लिया, पर कहीं पे भी वो सेंसर, लाइट का सेंसर है वो पर्टिकुलर वो नहीं ले रहा, बिकॉज स्कूल में यहाँ पे वो लोग यूज नहीं करते स्कूल्स में मेजरली. तो वो सेंसर कहीं पे नहीं मिला. बाद में एक इलेक्ट्रिशियन जो अंकल थे, मतलब उन्होंने बोला कि फोन में भी ऐसा सेंसर अगर बहुत इंपॉर्टेंट ना हो, अगर खरीदना ना हो, बिकॉज सेंसर इज अबाउट 2 or 3,000 रुपीज, तो अगर वो खरीदना ना हो तो फोन से भी हो सकता है. तो मैंने फोन से तभी के तभी खोल के फोन से ट्राई किया और ये ऐप डाउनलोड करके देखा, तो ऑब्वियसली यस, तो फोन वाज एब्सोल्युटली वर्किंग और वो इजीली हो सकता था. बट उसके बाद वापस एक चैलेंज आया कि जो सेंसर था फोन का, सॉरी, उसका एरिया बहुत छोटा था, प्लस जो एरिया बहुत छोटा था, प्लस उसमें फ्लक्चुएशन बहुत ज्यादा थे. अगर छोटी सी भी लाइट इधर के उधर हो गई तो उसमें फ्लक्चुएशन, मतलब वो एक्यूरेट बहुत था बट उसमें फ्लक्चुएशन बहुत ज्यादा आते थे, बिकॉज उसका एरिया एक तो छोटा था, तो उसकी वजह से इंटेंसिटी में बहुत वेरिएशन आता था. सो उसके लिए तो मुझे फर्स्ट उसको देखना था कि सेंसर किधर है उसका. सो सेंसर देखने के लिए भी मैंने प्रिसाइसली उस पे बाद में टाइम टू टाइम मैंने उस पे लेजर इंसिडेंट किया वो जो इतने एरिया पे, तब मुझे देख पता मिला कि मेरा सेंसर इधर है, और मैंने उसको मार्क करके रखा था या फिर मैंने याद रखा था कि इतने डिस्टेंस पे मेरा सेंसर है. उसके बाद आया वापस के उसको मैं स्टेबलाइज कैसे करूँ. जैसे मैंने हाँ, बाद में मैंने सेटअप तो पूरा रेडी कर लिया था कि चलो मेरे पास सेंसर भी है, ये भी है. बाद में फ़ोन वाला प्रॉब्लम आया कि फ़ोन को मैं स्टेबलाइज कैसे करूँ, कि मुझे उसको पकड़ के रखना पड़े. तो उसके लिए बाद में ये सोप केस वाला आइडिया है कि सोप केस को कट करके उसमें फ़ोन डाल सकते हैं अपन, और बाद में मैंने सेलो टेप मार दिया उसको. बट अभी भी प्रॉब्लम आया कि वो फ़ोन गिर जा रहा था, सेंटर ऑफ मास का बैलेंस नहीं था तो गिर जा रहा था. तो उसके लिए मैंने क्या कि वो खिल्ली आती बहुत मोटी-मोटी खिल्ली को मैंने चिपका दिया दूसरी साइड, मतलब बाँध के एकदम टाइटली, और उसके बाद उसको सेलो टेप कर दिया. तो वापस से उसका सेंटर ऑफ मास जो है बैलेंस हो गया, तो उसकी वजह से वो पूरा अपने आप में स्टेबल हो गया. बाद में एक और चैलेंज आया था कि लेज़र को मैं कैसे ऑन रखूँ, बिकॉज़ वो स्विच लेज़र थी, तो उसके लिए मैंने उसको सेलो टेप कर दिया, मैंने टाइट सेलो टेप मार दी, तो वो एकदम से मतलब कंटीन्यूअस लाइट देती रहे. बस बाद में, और उसके बाद प्रॉब्लम सबसे बड़ा प्रॉब्लम उसकी मेज़रमेंट में ही आया, बिकॉज़ एक तो कि अपने मतलब अपन जैसे मैंने बोला था कि रिफ्लेक्टेड इंटेंसिटी हमको चाहिए और ट्रांसमिटेड भी चाहिए, क्योंकि रिफ्लेक्टेड हमको इनिशियल इंटेंसिटी के बारे में बताएगा कि हमको माइनस करना पड़ेगा टोटल में से. तो उसको जब मैं सेंसर को इधर से इधर लेके आता था, तब बहुत ध्यान रखना पड़ता था क्योंकि पूरा सेटअप हिल जाता था, और लेज़र पूरी सिलिंड्रिकल थी, तो थोड़ा-सा भी मूवमेंट होने पे लेज़र खुद अपने आप में हिल जाती थी. तो यस, दिस वाज़ द थिंग. ये 3 मेजर चैलेंजेस थे. बाकी सेंसिटिव मतलब वो स्टेबल रखने के लिए बहुत प्रॉब्लम हो रहा था कि जो पूरा सेटअप है उसको स्टेबल रखने में। दिस वाज द थिंग ऐसा।
Amazing.
मस्त था तो यस था सेटअप. It was truly good. Great.
Well deserving for NCIP.
યસ
ઘણાને ખબર નહીં હોય પણ આ યશનો પ્રોજેક્ટ છે તે NCIP માટે સિલેક્ટ થયો છે 2020 જે થોડાક ટાઈમમાં ઇન્દોરમાં થવાની છે.
Congratulations.
Thank you for that. Anything else?
બીજા કોઈને કઈ ક્વેશ્ચન છે?
Anything related to light itself? ये फिनोमेना की नहीं पर लाइट के हिसाब से भी कुछ भी मतलब लाइट के रिलेटेड भी कुछ भी डाउट हो तो वो भी डिस्कस कर सकते हैं. थैंक यू उत्तम भाई.
કોઈને ક્વેશ્ચન है तो આપણે કન્ક્લુડ કરીએ. Thank you Yash, for such an amazing talk. We enjoyed a lot, got to know so many new things from you.
Thank you.
We would like to request USF to organize such events regularly. FTIR such amazing. પહેલા આપણે યશનો અરે જયનો જોયો, હવે યશનો જોયો, એના કરતા રહીએ તો ઘણી મજા આવે છે. દર સન્ડે આપણે કરીએ છીએ એમાં.
Yes.
Thank you so much for joining.
Thank you.
લાગે હવે બધા ઘરના જ છે.
હા આપણે ઘરના જ છે.
Exactly.
પેલા માટે સોરી યસ, મારો એવો મીનિંગ નહીં હતો. પેલું ઇંગ્લિશ મેં તને હિન્દીમાં કીધું. આ તો તને થોડીક આમ કેચી રહે.
એકચ્યુઅલી થોડોક પણ પ્રોબ્લેમ છે. આમે હિન્દીમાં બોલું જ ને તો બી એવું થાય.